Hello, good morning everyone. In previous lecture we studied definition of pointwise convergence and some example based on pointwise convergence. In this lecture we recall definition of pointwise convergence and some example on pointwise convergence. Then we see definition of uniform convergence. Okay, define f is a function from D to f is a function from D to R such that f of t equal to limit of n tending to infinity fn t is equal to lt for all t belongs to D. Since f of t equal to limit of n tending to infinity fn t, therefore f is well defined. Okay, let fn is the sequence of function defined on D and f is a function defined on D. If for any epsilon positive there exists and epsilon t belongs to natural number such that mod of fn t minus f of t less than epsilon for all n greater than equal to n epsilon t, then we say sequence fn converges pointwise to f. This is the definition of pointwise convergence. If we have a sequence fn and for given epsilon positive there exists n epsilon t belongs to natural number such that mod of fn t minus f of t less than epsilon for all n greater than equal to n epsilon t and depends on the epsilon and t for fixed values of t, this sequence is convergent. Then we say sequence fn t converges pointwise to f. This is a pointwise limit. This is a pointwise limit. That means limit of fn t equal to fn t. This means limit of n tending to infinity fn t is equal to f of t. In notation we write fn converges to f. This is notation for pointwise convergence. This is notation for pointwise convergence. This sequence is pointwise convergent. If there exists at least one point t naught belongs to D such that limit of n tending to infinity fn t naught does not exist, then we say limit sequence fn t does not converge pointwise if there exists at least one point and limit of fn t naught does not exist, then we say sequence fn t is not convergent at x is equal to t naught if there exists at least one point and t naught contain in t naught is an element of D, then sequence of function is not pointwise convergent. If convergent each point of t belongs to D, then we say sequence is pointwise convergent. Otherwise no. See example. Fn t equal to t to the power n for all t belongs to closed interval 0, 1. If t equal to 0, then f of fn t equal to 0. If t belongs to open 1, open at 0 and open 1 and t to the power n, and t belongs to 0 to 1 and limit of n tending to infinity fn f of t equal to 0, and if t is equal to 1, then fn 1 is equal to 1 to the power n, that means 1. That means limit of fn t equal to 1. This is a pointwise limit. This is a pointwise limit. That means sequence of function fn t equal to t to the power n converges pointwise. And example number 2, fn t equal to t to the power n by n factorial for all t belongs to closed interval 0, 1 since t belongs to, for fixed values of t, f and t tending to 0, because if you choose any values of t belongs to closed interval 0, 1, then f and t tending to 0 and n tending to infinity, as n tending to infinity. That means sequence of function f and t is pointwise convergent. And example number 3, f and t equal to sin n t. T belongs to closed interval 0, pi. If you take t equal to pi by 2, then fn pi by 2 equal to sin n pi by 2, and f of n fn pi by 2 equal to 1 when n equal to 1, sin of pi by 2 is equal to 1. Sin of pi by 2, n is equal to 1, then sin of pi by 2 is equal to 1. N is equal to 2, sin of 2 pi by 2, this is sin of pi. Sin n pi is 0, sin pi is 0. And n is equal to 3, n is equal to 3, sin 3 pi by 2, sin 3 pi by 2 is minus 1. And see this. This is y axis, this is x axis. If values of theta lies on y axis, positive y axis, values of sin is 1, and if lies negative y axis, values of sin is minus 1. And theta is equal to n pi. If theta is equal to n pi means lies on this, then sin theta is equal to 0. If theta is equal to n pi, at n pi, sin theta is 0. If theta is equal to odd pi by 2, n plus 1 pi by 2, then sin theta is plus minus 1. Sequence fn pi by 2 has 3 limit points, 1, 0 and minus 1. In sequence fn pi by 2 has 3 limit points. We already know if sequence has more than one limit point, then sequence is not convergent. Therefore, sequence fn pi by 2 is not convergent. If there exists at least one point where sequence fn t naught is not convergent, then sequence of function is not pointwise convergence. That's why sequence fn t is not pointwise convergent on closed interval 0, pi. Now lecture, अब हम लोग लेक्चर 2 स्टार्ट करते हैं, और यहाँ पर एक एग्जांपल और देखते हैं हम लोग. एग्जांपल, fn nth term fn x equal to 1 plus x बटा n to the power n for all x belongs to real number. This sequence is convergent to e to the power x. Sequence fn x equal to, see, first term, what is first term? 1 plus x, n is equal to 1, then 1 plus x, n is equal to 2, 1 plus x bata 2 whole square, n is equal to 3, 1 plus x bata 3 whole cubic, so on. Nth term 1 plus x bata n to the power n, so on. This is a sequence, first term of the sequence, second term of sequence, third term of sequence, and nth term of sequence. For any fixed values of real number, for any x belongs to real number, limit of n tending to infinity fn x equal to limit of n tending to infinity 1 plus x bata n to the power n. This is equal to e to the power x, which is finite less than infinity. For fixed values of x, this is finite and less than infinity. Less than infinity means finite. That means sequence fn x converges to f of x. Fx means e to the power x. Pointwise. This convergence is pointwise. Observe that sequence fn, each term of the sequence is unbounded. Each term of the sequence is unbounded. For any fixed n belongs to natural number. Suppose n is equal to 1. f1x is equal to 1 plus x. For all x belongs to real number. f1x is unbounded because x belongs to real number. This is a straight line and this is unbounded. And n is equal to 2. f2x 1 plus x bata 2 whole square. This is a polynomial for all x belongs to real number. This is also unbounded. This is a sequence of unbounded function, but sequence of function is pointwise convergent. Sequence of function is a pointwise convergent. This is some observation. If sequence of term may be unbounded, but sequence is convergent. Each term of the sequence is a polynomial. That's why sequence is unbounded. Sequence of term is unbounded. Sequence is not unbounded. Sequence of term is unbounded. Now see in the next example. Gn x equal to x square plus 1 bata n for all n belongs to natural number and x belongs to real number. X belongs to real number. For any fixed values of x, for any fixed values of x, for any fixed x belongs to real number, limit of n tending to infinity gn x is equal to x square. Let gx. Okay, this sequence is pointwise convergence. Sequence gnx converging to gx pointwise. Which type? Pointwise. This sequence is pointwise convergent to x squared. But for any fixed values of n, this sequence of term of the sequence is unbounded. For any fixed, for any n belongs to natural number, gn x is not bounded. Suppose if f is a function from d to r and if there exists t naught belongs to d such that sequence is unbounded. For fixed values of t, is sequence is unbounded, then sequence is not convergent. Now see one note. Okay. Note. Suppose we already studied in the sequence of real number. Sequence is convergent. Then sequence has unique limit point and it is bounded. If for fixed values of t sequence of real number is unbounded, then at, at that point sequence is not convergent. That means if there exists at least one point where the sequence of real number is unbounded, then sequence of is not pointwise convergent. Suppose if fn is a function from D to R, if there exists T naught belongs to real number, T naught belongs to domain, T naught belongs to D such that sequence fn at T naught n is equal to 1 to infinity is unbounded, is now write the term of the sequence f1 T naught at T naught, okay, f2 T naught, so on fn T naught. If this sequence is unbounded, then sequence of function is not pointwise convergent. If this sequence is unbounded, is not bounded. In short, BDD, okay, implies sequence of function is not pointwise convergent. This sequence is not pointwise convergent. Now see the necessary and sufficient condition, or when you say sequence, if sequence is pointwise convergent, suppose sequence is pointwise convergent, then what is a necessary condition? Then what is a necessary condition? If sequence of function is pointwise convergent, then what is a necessary condition? We have to find the necessary condition when the sequence of function is pointwise convergent. Necessary condition for pointwise convergence. Pointwise convergence. Let fn be the sequence of function from D to R such that sequence fn converges pointwise. Let sequence be a sequence of function fn is a function from D to R converges pointwise. Pointwise to F. Then for any T belongs to real number, for any T belongs to D from domain, T belongs to D from domain, the sequence fn T for fixed values of T is bounded. Is bounded. That means there exists mt for fixed values of T. There exists mt belongs to real number such that mod of fnt is less than equal to mt for all n belongs to natural number. This is a necessary condition for pointwise convergence. Example. Now see the example. Let fnx equal to nx. Okay, and x for all x belongs to close interval 0, 1. For fixed values of x, this sequence is not bounded. That means we directly say that sequence fn is not pointwise convergent. For n is equal to, suppose n is equal to x is equal to 1 by 2. Fn 1 by 2 equal to n by 2. This is not bounded. This is tending to infinity. As n tending to infinity, this sequence of function for fixed values of x is not bounded. That means this sequence implies this sequence fn x is equal to nx does not converge pointwise. Does not converge pointwise. Also, if there exists t naught belongs to D, sequence fn t naught has two limit points. And next note, if there exists t naught belongs to D from domain of the function, sequence fn t naught, this is a sequence of real number for fixed values of x, for fixed values of t belongs to D, this is a sequence of real number, has two limit point, has two limit point, yeah, more than two limit point, more than one limit point, two limit point, three limit point, two limit point, yeah, more than one limit point. We say we can conclude that sequence fnx does not converges pointwise. Now see example based on this note. Example. Suppose let fn t equal to t to the power n on -1, 1. For t is equal to -1. For t is equal to -1, fn -1 equal to -1 to the power n, -1 to the power n has two limit point. This sequence has two limit point. Two limit point. That means this sequence therefore implies sequence fnx does not converge pointwise. On -1, 7. But this sequence is converged if you consider let fnx equal to t to the power n and t belongs to open -1, open at -1 and close at 1. For any values of x, for any x belongs to open -1 at 1, sequence fnx tending to 0 when x belongs to -1 to 1 and 1, x is equal to 1. That means this sequence is pointwise convergent on this sequence is pointwise convergent. Sequence fnx equal to t to the power n is pointwise convergent. Pointwise converge on open minus 1 close 1. But if you can include minus 1, then at minus 1 t is equal to minus 1, fn x has two limit points 1 and minus 1. Therefore this sequence is not convergent pointwise on closed interval minus 1 comma 1, but this sequence is pointwise convergent on open at minus 1 comma 1 close at 1. Okay, thank you. If you have your preparation, this lecture is helpful for your preparation, then like this video and comment. Thank you. Okay, bye bye.